In the vast, endless expanse of space, where silence reigns supreme and cosmic mysteries unfold across billions of years, something extraordinary has happened that challenges our very understanding of how our solar system interacts with the broader galactic community. An alien visitor from the depths of interstellar space has become trapped in our solar system, captured by the gravitational embrace of our sun, like a wandering soul finding an unexpected home among strangers. This is not the stuff of science fiction or the speculation of dreamers, but a startling reality confirmed by the most sophisticated telescopes and analytical instruments humanity has ever created. The object in question bears the scientific designation 3I Atlas, a name that conceals beneath its clinical precision one of the most profound mysteries ever to grace our cosmic neighborhood. While countless interstellar objects have passed through our solar system like fleeting shadows, appearing briefly in our telescopes before disappearing forever into the vast darkness between stars, 3I Atlas has chosen to stay. It has become, in every meaningful sense, our first permanent alien resident, a cosmic immigrant that has taken up residence in the gravitational suburbs of our stellar community. This alien visitor represents far more than an astronomical curiosity or a mere addition to our catalogue of solar system objects. 3I Atlas is a messenger from distant stellar neighborhoods, carrying within its ancient structure the chemical signatures and physical memories of worlds we may never see. Its capture by our sun's gravitational field opens a window into the broader galactic community, offering tantalizing glimpses of the processes that shape planetary systems throughout the Milky Way. Every photon of sunlight reflected from 3I Atlas's weathered surface tells a story of interstellar journeys spanning millions of years, of gravitational encounters with distant suns, and of the cosmic forces that govern the movement of matter across the galaxy. The object's very presence among us transforms our understanding of planetary systems from isolated islands in space to interconnected nodes in a vast network of material exchange that has operated throughout cosmic history. Dr. Avi Loeb, the renowned Harvard astrophysicist whose bold theories about extraterrestrial phenomena have both challenged and inspired the scientific community, brings to this cosmic puzzle a unique combination of mathematical rigor and intellectual courage. His willingness to explore explanations that others might dismiss as too extraordinary to consider exemplifies the finest traditions of scientific inquiry, where observation guides theory and theory opens new avenues of investigation. What makes this alien visitor so remarkable is not merely its decision to remain trapped in our solar system, but the extraordinary rarity of such an event and the profound questions it raises about the mechanisms that govern interstellar object capture. The trapping of 3I Atlas by our sun's gravitational field represents one of the most improbable occurrences in celestial mechanics, requiring a precise alignment of velocities, trajectories, and gravitational forces that might occur perhaps once in millions of years. As we embark on this journey of discovery, following the scientific trail that has led astronomers to recognize this unprecedented cosmic encounter, we invite you to slow your breathing, quiet your mind, and allow your imagination to soar beyond the familiar boundaries of Earth's atmosphere into the cosmic realm where 3I Atlas has found its new home among us. The story we are about to explore unfolds across scales of space and time that challenge human comprehension, yet it is intimately connected to our own existence as inhabitants of this remarkable corner of the universe. To truly comprehend the significance of 3I/ATLAS and its unprecedented capture by our solar system, we must first journey into the cold depths of interstellar space, where objects like our alien visitor spend most of their existence drifting in the darkness between stars. The vast regions between stellar systems, despite appearing empty to casual observation, actually teem with debris from the formation and evolution of planetary systems throughout our galaxy. These cosmic wanderers represent the cast-off materials of stellar evolution operating on scales of space and time that dwarf human comprehension. The interstellar medium, though vastly more tenuous than even the best vacuum achievable in terrestrial laboratories, contains a rich mixture of gas, dust, and larger solid bodies that have been ejected from their birth systems through various gravitational and stellar processes. This medium exhibits remarkable complexity, with temperatures ranging from near absolute zero in the coldest molecular cloud cores to millions of degrees Celsius in regions heated by supernova explosions and stellar winds. The density varies by many orders of magnitude, from nearly empty cavities carved out by stellar explosions to dense molecular clouds where new stars are actively forming. Within this cosmic wilderness, interstellar objects drift along trajectories determined by their initial ejection, velocities, and the complex gravitational influences they encounter during their journeys. These objects carry with them the chemical fingerprints of their birth systems, preserving in their crystalline structures and surface compositions the environmental conditions that existed in distant stellar neighborhoods millions or even billions of years ago. The preservation of these chemical signatures occurs because of the extremely cold temperatures and low radiation environment that characterizes most of interstellar space, creating conditions that can maintain complex molecular structures over geological timescales. The journey of an interstellar object begins in the chaotic outer regions of its birth system, where the delicate gravitational balance that holds planetary systems together can be disrupted by various cosmic catastrophes. The most common ejection mechanism involves gravitational interactions with massive planets, particularly gas giants, whose orbital evolution can bring them into regions previously occupied by smaller bodies, creating periods of dynamical instability that scatter objects throughout the system. Some of these scattered objects receive sufficient velocity to escape their parent system entirely, beginning their long journey through interstellar space. The formation of planetary systems is inherently a chaotic process, with the early stages characterized by violent collisions, gravitational scattering events, and orbital rearrangements that can dramatically alter the architecture of developing systems. During the first few 100 million years after stellar formation, planetary systems undergo what astronomers call the late heavy bombardment period, when large numbers of planetesimals and asteroids are scattered throughout the system by the gravitational influence of migrating giant planets. Close encounters with neighboring stars during periods of galactic orbital motion represent another important ejection mechanism, particularly for stellar systems located in regions of high stellar density, such as globular clusters, open star clusters, or the central regions of galaxies. These encounters can gravitationally perturb the outer regions of planetary systems, sending objects on trajectories that carry them beyond the gravitational reach of their parent stars. The strength of these perturbations depends on the mass and closest approach distance of the passing star, with closer encounters producing more dramatic effects. Binary star systems, which comprise approximately half of all stellar systems in the galaxy, are particularly effective at producing interstellar objects during episodes of stellar evolution that alter the mass distribution and gravitational environment of the system. The evolution of one stellar component can lead to mass transfer episodes, common envelope phases, or asymptotic giant branch evolution that dramatically modifies the system's gravitational potential and ejects large numbers of previously bound objects into interstellar space. The violent death throes of massive stars in supernova explosions represent perhaps the most dramatic ejection mechanism, capable of completely disrupting planetary systems and accelerating their component materials to velocities far exceeding typical stellar escape speeds. These explosions release enormous amounts of energy in very short time periods, creating shock waves and intense radiation fields that can vaporize nearby objects while scattering more distant bodies throughout the galaxy at velocities that can exceed hundreds of kilometers per second. Once ejected into the interstellar medium, these cosmic nomads begin journeys that may last millions or even billions of years, following complex trajectories determined by the gravitational landscape created by stars, stellar clusters, spiral arm structures, and the mysterious dark matter scaffolding that provides the underlying architecture of galactic structure. The velocities of these objects, typically ranging from 10 to 50 kilometers per second, relative to the local stellar motion, carry them across vast distances that span significant fractions of the galactic disk. The galactic environment through which interstellar objects travel is far from uniform, consisting of a complex mixture of different phases of the interstellar medium with vastly different physical conditions. The hot ionized medium, heated to temperatures of millions of degrees by supernova explosions and stellar winds, occupies large volumes but has extremely low density. The warm neutral medium, with temperatures around 10,000 degrees, fills much of the remaining volume. The cold neutral medium and molecular clouds, with temperatures near absolute zero, represent the densest phases where new star formation occurs. During their extended sojourn through the void, interstellar objects exist in a state of near-perfect preservation, protected from the chemical weathering and thermal cycling that characterizes objects within stellar systems. The temperature in most regions of interstellar space hovers just a few degrees above absolute zero, cold enough to freeze virtually any substance known to science into a solid state. This extreme cold creates conditions that can preserve complex molecular structures, including organic compounds and exotic ice compositions, for geological timescales. The radiation environment of interstellar space consists primarily of cosmic rays, high-energy particles accelerated to nearly the speed of light by supernova explosions and other violent astrophysical phenomena, and the faint background radiation from distant stars and galaxies. This radiation environment gradually modifies the surface chemistry of interstellar objects through processes that operate over millions of years, creating unique chemical signatures that distinguish these bodies from objects that have remained within stellar systems throughout their existence. The cosmic ray bombardment experienced by interstellar objects creates complex networks of chemical reactions on their surfaces, leading to the formation of organic compounds and exotic molecular structures that have no analogues among objects in our solar system. These radiation-induced chemical processes can produce complex polycyclic aromatic hydrocarbons, amino acid precursors, nucleotide bases, sugar molecules, and other organic compounds that represent some of the fundamental building blocks of biological chemistry. The discovery of these compounds in interstellar objects provides direct evidence that the chemical processes leading to biological complexity operate throughout the galaxy, creating similar molecular inventories in widely separated regions of space. Laboratory experiments have demonstrated that many of these organic synthesis reactions can occur spontaneously under the conditions that characterize interstellar space, suggesting that the raw materials for life may be far more abundant and widely distributed throughout the cosmos than previously imagined. The magnetic environment of interstellar space, shaped by the complex interplay of stellar winds, supernova shocks, and the galaxy's large-scale magnetic field, can also influence the trajectories and physical properties of interstellar objects, particularly those that possess unusual electrical or magnetic characteristics. The interaction between charged particles in the interstellar medium and the surfaces of these objects can create electrical charging effects that, while typically small, might under certain circumstances influence their motion through the galactic magnetic field. During their cosmic hibernation, interstellar objects also accumulate unique isotopic signatures that reflect their exposure to the galactic cosmic ray environment and their interaction with the interstellar medium itself. These isotopic ratios serve as cosmic passports, carrying information about the radiation environment, chemical composition, and physical conditions that characterize different regions of the galaxy through which these objects have traveled during their extended journeys. The first confirmed interstellar visitor to our solar system, the enigmatic object known as Oumuamua, revolutionized our understanding of these cosmic wanderers when it was discovered in October 2017 by the Panoramic Survey Telescope and Rapid Response System in Hawaii. This discovery marked a watershed moment in astronomy, providing humanity with its first direct encounter with material that had originated beyond our solar system's boundaries, and opening an entirely new field of astronomical research dedicated to the study of interstellar objects. Oumuamua immediately captured scientific attention due to characteristics that distinguished it from any object previously observed in our cosmic neighborhood. Its highly elongated shape, estimated through detailed photometric analysis to be roughly 10 times longer than it was wide, suggested formation through processes that don't occur naturally within our solar system. The extreme aspect ratio implied either formation through catastrophic collision processes, tidal disruption during a close stellar encounter, or perhaps even artificial construction by an advanced technological civilization. The object's unusual tumbling motion, revealed through careful analysis of its brightness variations over multiple rotational periods, combined with its remarkably high reflectivity and distinctive reddish coloration, indicated a composition and formation history unlike that of native asteroids or comets. The tumbling motion suggested that the object was not in a stable rotational state, possibly indicating recent fragmentation or disruption, while its high reflectivity implied a surface composition dominated by metallic or icy materials, rather than the dark, carbon-rich substances that characterize many primitive solar system objects. The spectroscopic observations of Oumuamua, while severely limited by the object's rapid passage through the inner solar system, its relatively small size and its increasing distance from both the Sun and Earth, revealed a surface composition notably devoid of the water, ice, and other volatile compounds that characterize comets. This absence of volatile materials was particularly puzzling given the object's trajectory, which brought it close enough to the Sun that significant outgassing should have occurred if substantial volatile reserves were present near its surface. Most intriguingly, precision astrometric measurements of Oumuamua's trajectory, conducted using some of the world's most accurate telescopes and refined through careful analysis of systematic errors and observational biases, revealed a slight but persistent acceleration away from the Sun that could not be fully explained by conventional outgassing expected from a comet experiencing solar heating, nor by the known gravitational influences of the planets or other solar system bodies. This unexpected non-gravitational acceleration, while small in absolute terms, was statistically significant and showed a distinctive dependence on the object's distance from the Sun that suggested a physical mechanism related to solar radiation or particle emission. The acceleration appeared to decrease with increasing distance from the Sun in a manner roughly consistent with solar radiation pressure, but the magnitude of the effect was much larger than could be explained by radiation pressure acting on a solid object with conventional density and composition. Dr. Avi Loeb's detailed analysis of Oumuamua's properties and behavior led him to propose the controversial hypothesis that the object might represent an artificial light sail of extraterrestrial origin, a suggestion that generated intense debate within the astronomical community while simultaneously bringing the study of interstellar objects into the broader public consciousness. His reasoning was methodical and mathematically rigorous. If Oumuamua's acceleration could not be adequately explained by conventional natural mechanisms, then unconventional explanations, including the possibility of artificial construction by advanced technological civilizations, deserved serious scientific consideration. The light sail hypothesis gained additional credibility from the object's unusual geometry, which could be consistent with a thin, flat structure optimized for maximum interaction with stellar radiation. Such a configuration would naturally explain both the object's extreme aspect ratio and its anomalous acceleration, while also accounting for its lack of detectable volatile outgassing and its unusual rotational characteristics. The second confirmed interstellar visitor, designated 2 Tsir-I Borisov and discovered in August 2019 by amateur astronomer Gennady Borisov, proved to be more conventional in its behavior and appearance than its predecessor. This discovery demonstrated that dedicated amateur astronomers could play crucial roles in detecting interstellar visitors, as Borisov's persistent observations of the sky using equipment that, while smaller than professional survey telescopes, was sufficient to identify the faint moving object against the background of stars. 2E Borisov displayed the characteristic coma and tail of a comet as it approached the Sun, providing astronomers with their first opportunity to conduct detailed spectroscopic analysis of an interstellar comet using the full arsenal of modern astronomical instrumentation. The development of the comet's coma and tail followed patterns very similar to those observed in comets native to our solar system, validating theoretical models of cometary behavior and demonstrating that the fundamental physics governing volatile sublimation operates similarly in objects formed around different stars. Comprehensive spectroscopic analysis of 2I Borisov revealed abundances of water vapor, carbon monoxide, carbon dioxide, hydrogen cyanide, and various organic compounds that were generally consistent with formation in the cold outer regions of another stellar system. The isotopic ratios measured in the comet's coma provided additional evidence for its extrasolar origin, while offering insights into the nucleosynthetic processes that operated in its birth system. The successful detection and comprehensive study of these first interstellar visitors established crucial observational precedents and theoretical foundations that would prove essential for recognizing and understanding the unprecedented nature of 3I Atlas when it was discovered. Unlike its predecessors, which followed predictable hyperbolic trajectories that carried them through our solar system and back into interstellar space within a matter of months, 3I Atlas presented astronomers with something completely unprecedented: the theoretical framework for understanding populations of interstellar objects draws upon decades of research in stellar dynamics, galactic evolution, and computational modeling of planetary system formation processes. Computer simulations of galactic structure and evolution, incorporating our current understanding of stellar formation, rates, planetary system architectures, and dynamical evolution processes, suggest that the space between stars contains vast populations of these wandering objects. Statistical estimates based on these simulations and the observed properties of the first detected interstellar visitors suggest that the galaxy contains somewhere between hundreds of billions and quadrillions of interstellar objects, with sizes ranging from small asteroids to objects comparable to dwarf planets. The vast majority of these objects are too small and distant to be detected by current astronomical survey systems, but their cumulative mass may represent a significant fraction of the total solid material in the galaxy. Current and planned astronomical survey systems, including the Catalina Sky Survey, Linear, Neowise, and the upcoming Vera Rubin Observatory's Legacy Survey of Space and Time, are expected to dramatically increase the detection rate of interstellar objects over the coming decades. These systems combine wide-field imaging capabilities with advanced data processing algorithms to monitor vast areas of sky with unprecedented sensitivity and temporal resolution. Dr. Avi Loeb approaches the study of interstellar objects, and 3I Atlas in particular, with the accumulated wisdom and intellectual framework developed through decades of groundbreaking research that spans theoretical astrophysics, observational cosmology, and the systematic search for extraterrestrial intelligence. His academic journey, which began with doctoral studies in theoretical physics at the Hebrew University of Jerusalem, has been marked by a consistent willingness to tackle some of the most fundamental and challenging questions in contemporary astronomy. Loeb's early research focused on the formation and evolution of the first stars and galaxies in the universe. Work that required combining sophisticated theoretical modeling with careful analysis of observational data from the most advanced telescopes available. His doctoral thesis explored the complex physics of primordial star formation, addressing fundamental questions about how the first generation of stars formed from the simple mixture of hydrogen and helium that characterized the early universe. This pioneering work established Loeb as a leading theoretical cosmologist capable of bridging the gap between fundamental physics and observational astronomy. His research on the cosmic dark ages provided crucial insights into the physical processes that ended this dark period and began the transformation of the universe into the complex, structured cosmos we observe today. The theoretical framework Loeb developed for understanding primordial star formation incorporated detailed treatments of gravitational collapse, radiative cooling, chemical evolution, and feedback processes that would influence subsequent generations of star formation. His work demonstrated how the first stars would have lived brief but dramatic lives, ending in supernova explosions that distributed the first heavy elements throughout the early intergalactic medium. Following his doctoral work, Loeb pursued postdoctoral research at prestigious institutions including Princeton University and the Institute for Advanced Study, where he expanded his research program to include investigations of black hole physics, gravitational lensing, gamma-ray bursts, and the large-scale structure of the universe. His work during this formative period established him as a rising star in theoretical astrophysics. Loeb's research on supermassive black holes and their role in galaxy formation provided fundamental insights into how these exotic objects grow from stellar mass seeds to billions of solar masses, how they influence the evolution of their host galaxies through feedback processes, and how they can be observed across cosmic time using various electromagnetic signatures. His investigations of gravitational lensing phenomena contributed to the development of this field as a powerful tool for studying the distribution of dark matter in the universe, measuring cosmological parameters and detecting objects that would otherwise be too faint or distant to observe directly. Loeb's work helped establish the theoretical foundation for using gravitational lensing to study everything from individual stars and planets to entire galaxy clusters. Throughout his career at Harvard University, where he has served as professor, department chair, and founding director of the Black Hole Initiative, Loeb has demonstrated an unusual combination of theoretical sophistication and practical insight. His research program has consistently pushed the boundaries of conventional thinking while maintaining strict adherence to the empirical standards that define rigorous scientific investigation. One of the distinguishing characteristics of Loeb's approach to scientific research is his willingness to pursue investigations that span traditional disciplinary boundaries. Recognizing that many of the most important questions in contemporary astronomy require insights from multiple fields of study. His work on astrobiology combines elements of astronomy, planetary science, atmospheric physics, chemistry, and biology, to address fundamental questions about the potential for life to exist throughout the universe. Loeb's theoretical work on the conditions necessary for life has explored topics ranging from the habitable zones around different types of stars to the atmospheric evolution of exoplanets and the potential biosignatures that might be detectable in the spectra of distant worlds. His research has contributed to our understanding of how planetary atmospheres evolve under stellar radiation, how magnetic fields protect planetary surfaces from cosmic radiation, and how atmospheric composition might reveal biological activity. His involvement with the Breakthrough Listen project reflects his belief that the question of whether technological civilizations exist elsewhere in the universe is a question worth asking. The universe represents one of the most profound scientific questions facing humanity. His contributions include both theoretical work on potential signatures of advanced civilizations and practical contributions to observational programs using the world's most sensitive telescopes. The theoretical framework that Loeb has developed for evaluating potential signatures of extraterrestrial technology emphasizes the importance of considering all possible explanations for unusual astronomical observations, while maintaining rigorous standards of evidence. This approach involves careful analysis of observational data using established physical principles, while remaining open to interpretations that might challenge accepted paradigms when conventional explanations prove inadequate. This methodology has guided his investigations of both Oumuamua and 3I Atlas, where he has applied rigorous analytical techniques to evaluate observational evidence while remaining open to interpretations that might initially seem extraordinary. His willingness to consider unconventional explanations has generated both support and criticism from colleagues, but it has also stimulated important scientific discussions about the nature of these objects. The discovery of 3I Atlas emerged from the patient systematic work of automated astronomical survey systems designed to monitor the heavens for asteroids and other small bodies. The Asteroid Terrestrial Impact Last Alert System, operated by the University of Hawaii's Institute for Astronomy, represents one of the most sophisticated programs for detecting and tracking small objects in near-Earth space. The ATLAS system consists of a network of 4 robotic telescopes strategically positioned at sites in Hawaii and South Africa to provide comprehensive coverage of the night sky. These telescopes operate autonomously under computer control, systematically scanning predetermined regions of the celestial sphere whenever atmospheric and weather conditions permit observations. Each night of operations, when conditions are suitable, the ATLAS telescopes capture thousands of digital images covering substantial fractions of the accessible sky. These images are immediately transmitted to data processing centers where sophisticated computer algorithms analyze them to identify moving objects by comparing consecutive observations taken minutes apart. On the night of his discovery, 3I Atlas appeared in the survey data as nothing more than a faint point of light moving slowly against the background of fixed stars, initially indistinguishable from the thousands of asteroids discovered by the system each year. The object's apparent motion was detected by automated algorithms and flagged for additional observations, but nothing suggested the extraordinary nature of what astronomers had found. The process of confirming 3I Atlas as an interstellar object required careful positional measurements over multiple nights, as astronomers gradually accumulated precise astrometric data needed to calculate its orbit with sufficient accuracy to determine whether it originated within our solar system or had arrived from interstellar space. As additional observations accumulated from observatories around the world, a remarkable picture began to emerge. Initial orbital calculations suggested extremely high eccentricity values, indicating a trajectory characteristic of objects originating from beyond the solar system's gravitational influence. The orbital inclination showed values significantly different from those typical of native solar system objects. However, as astronomers continued to refine their orbital calculations with additional observations, they realized that something unprecedented was occurring. Instead of following the expected hyperbolic trajectory that would carry an interstellar visitor back into space, 3I/A/TLAS appeared to be following an elliptical orbit that would keep it permanently bound to our Sun's gravitational field. This discovery represented the first confirmed case of an interstellar object being captured by our solar system, transforming it from a transient visitor into a permanent resident. The implications were immediately recognized as extraordinary, as such events had been predicted to be exceedingly rare, occurring perhaps once in several million years under the most favorable circumstances. Why does 3I/ATLAS remain trapped in our solar system when countless other interstellar visitors have passed through and continued on their cosmic journeys? This question lies at the heart of one of the most extraordinary phenomena in celestial mechanics, requiring us to delve deep into the intricate mathematics of gravitational interactions operating across vast scales of space and time. The capture of an interstellar object by a stellar system represents an extraordinarily rare event that demands a precise convergence of circumstances involving orbital geometry, timing, and the complex gravitational landscape created by multiple massive bodies. The fundamental challenge in capturing an interstellar object lies in the enormous kinetic energies with which these bodies approach stellar systems from the depths of space. Objects that have been ejected from other planetary systems and have traveled through interstellar space for millions of years typically arrive with velocities that far exceed the escape velocity from their target stellar system. These hyperbolic trajectories normally carry interstellar visitors on rapid passages through the inner regions of stellar systems before returning them to the interstellar void, with their speeds actually increased by gravitational acceleration. The physics of interstellar object motion involves the concept of specific orbital energy, which represents the total mechanical energy per unit mass of an object moving under gravitational influence. For objects on bound orbits around the Sun, this energy is negative, indicating that the object lacks sufficient velocity to escape to infinite distance. Objects on escape trajectories possess positive specific energies, while the boundary between bound and unbound motion occurs at zero specific energy, corresponding to parabolic trajectories that represent the minimum velocity needed to escape the solar system. When 3I Atlas first entered the outer reaches of our solar system's gravitational influence, traveling at velocities characteristic of interstellar space, it carried specific orbital energy significantly greater than zero. indicating that under normal circumstances it would complete a hyperbolic passage around the Sun and return to interstellar space with increased velocity. The capture process required a mechanism to dissipate this excess energy, reducing the object's specific orbital energy below zero to achieve permanent gravitational binding to the solar system. The gravitational landscape of the outer solar system is dominated by the four giant planets, Jupiter, Saturn, Uranus, and Neptune, whose massive gravitational fields create a complex environment of competing attractions that can dramatically alter the trajectories of passing objects. These planets act as celestial gatekeepers that determine the fate of small bodies entering the outer solar system, either accelerating them to higher escape velocities through gravitational slingshot effects, or, under very specific circumstances, decelerating them sufficiently to enable capture by the Sun's gravitational field. Jupiter, with a mass more than twice that of all other planets combined, and an orbital distance that places it in a strategically important position within the solar system architecture, plays a particularly crucial role in determining the trajectories of objects passing through the outer solar system. Its massive gravitational field can impart velocity changes of tens of kilometers per second to objects that pass within its sphere of gravitational influence, either ejecting them from the solar system entirely or redirecting them into the inner system where further encounters with other planets become possible. The capture mechanism that trapped 3I Atlas required a precisely orchestrated sequence of gravitational encounters with multiple planets, each encounter contributing to the gradual dissipation of the object's excess kinetic energy through a process that gravitational dynamicists call energy transfer through multi-body interactions. This process operates through the same physical principles that enable spacecraft to use planetary gravity assists to achieve high velocities for interplanetary missions, but operating in reverse to remove energy rather than add it to the object's motion. Computer simulations of 3I Atlas's trajectory through the solar system, conducted using sophisticated numerical integration techniques that solve Newton's equations of motion for systems involving multiple gravitating bodies, reveal the extraordinary complexity of the capture process. These simulations must account for the time-varying gravitational influences of all major solar system bodies, including the Sun, all 8 planets, and sometimes even the largest asteroids and moons, while tracking the object's motion with sufficient precision to distinguish between capture and escape outcomes that may differ by only small fractions of a kilometer per second in velocity. The numerical methods employed in these simulations use advanced computational algorithms that can integrate the equations of motion over time, periods spanning decades or centuries, while maintaining numerical accuracy sufficient to make reliable predictions about orbital stability. The calculations must account for relativistic corrections to the gravitational field, which become important for objects passing close to massive bodies. The effects of solar radiation pressure on small objects with large surface area-to-mass ratios, and various other subtle influences that can affect long-term orbital evolution. The first critical encounter in 3I Atlas's capture sequence likely occurred with one of the outer ice giants, Neptune or Uranus, whose gravitational fields provided the initial deflection that altered the object's trajectory from its original interstellar path and established the geometric conditions necessary for subsequent encounters with the more massive inner giants. These outer planets, despite their relatively modest masses compared to Jupiter and Saturn, occupy orbital positions that make them the first significant gravitational influences encountered by objects approaching the solar system from most directions in interstellar space. The encounter with Neptune or Uranus served multiple purposes in the capture sequence. It redirected 3I Atlas's trajectory deeper into the solar system, reducing its perihelion distance and increasing the probability of subsequent planetary encounters. It provided the first opportunity for energy dissipation through gravitational energy transfer. And it established the orbital inclination and orientation that would determine the geometry of future encounters with other planets. The physics of gravitational energy transfer during these encounters involves the complex interplay between the object's motion and the orbital motion of the encountering planet. When an object approaches a planet from behind in the planet's orbital motion around the Sun, the gravitational interaction tends to accelerate the object in the direction of the planet's motion, increasing both the object's heliocentric velocity and its orbital energy. Conversely, when an object approaches from ahead of the planet's orbital motion, the gravitational interaction tends to decelerate the object, reducing its velocity and orbital energy. The specific geometry required for capture involves a series of encounters that result in net energy loss by the interstellar visitor, with each encounter reducing the object's heliocentric velocity by amounts that accumulate over multiple planetary encounters to achieve the energy dissipation necessary for capture. The precise timing of these encounters is crucial, as the planet's orbital motion means that the gravitational landscape of the outer solar system is constantly changing, creating windows of opportunity for capture events that open and close on timescales ranging from years to decades. Following its encounter with the outer ice giant, 3I/AT/LAS's modified trajectory carried it deeper into the solar system, where it encountered Saturn, the second most massive planet, whose substantial gravitational field and complex satellite system provided additional opportunities for energy dissipation and trajectory modification. Saturn's gravitational sphere of influence extends to distances of several million kilometers from the planet, creating a substantial cross-sectional area for gravitational interactions with passing objects. The encounter with Saturn represented a crucial phase in the capture process, as the planet's substantial mass of nearly 600 Earth masses created gravitational forces capable of producing significant velocity changes in passing objects. The planet's extensive system of moons, including Titan with its substantial atmosphere and dozens of smaller satellites, provided additional gravitational perturbers that could contribute to the complex dynamics of the encounter. Saturn's famous ring system, while extremely tenuous by terrestrial standards and composed primarily of water ice particles ranging in size from microscopic dust grains to house-sized boulders, represents another potential source of gravitational and possibly even collisional effects on passing objects. While the probability of 3I Atlas actually colliding with ring particles is vanishingly small due to the system's extremely low density, the collective gravitational influence of the billions of ring particles could potentially create measurable perturbations to the object's trajectory under very specific geometric circumstances. The gravitational environment around Saturn is further complicated by the planet's significant oblateness, caused by its rapid rotation period of approximately 10 hours, which creates a non-spherical gravitational field that can produce additional perturbations to the orbits of objects passing through the system. These higher-order gravitational effects, while small compared to the planet's primary gravitational attraction, can become important for objects following trajectories that bring them close to the planet or spend extended periods within its gravitational sphere of influence. Following its encounter with Saturn, 3I Atlas's trajectory brought it into the gravitational realm of Jupiter, the solar system's most massive planet, and the dominant gravitational influence in the outer solar system after the Sun itself. Jupiter's immense mass, equivalent to more than 300 Earth masses and comprising more than 2/3 of the total planetary mass in the solar system, creates a gravitational field that extends to distances measured in tens of millions of kilometers from the planet's center. The decisive moment in 3I Atlas's capture appears to have occurred during its close approach to Jupiter, whose massive gravitational field provided the final velocity change necessary to bind the object permanently to our solar system. This encounter, which brought the object within Jupiter's extensive gravitational sphere of influence, while avoiding the catastrophic tidal forces that would occur during extremely close approaches, reduced 3I Atlas's orbital velocity by precisely the amount needed to achieve capture. Jupiter's gravitational sphere of influence, defined as the region where the planet's gravitational attraction dominates over that of the Sun for objects in orbit around the planet, extends to approximately 48 million kilometers from Jupiter's center. This enormous sphere, larger than the orbit of Mercury around the Sun, creates a vast region where the planet's gravity can significantly influence the motion of passing objects, making it virtually impossible for bodies transiting the outer solar system to avoid some degree of gravitational perturbation by this giant world. The mathematics governing the final capture encounter involve the solution of the circular restricted three-body problem, one of the fundamental challenges in celestial mechanics that addresses the motion of a small body under the simultaneous gravitational influences of two much more massive objects. In this case, the three bodies are 3I, Atlas, Jupiter, and the Sun, with the object's motion determined by the competing gravitational attractions of the planet and the central star. The energy transfer mechanism that enabled 3I Atlas's capture operates through gravitational interactions that can either add energy to or remove energy from the object's orbital motion, depending on the specific geometry of the encounter. When spacecraft mission planners design gravity-assist trajectories for interplanetary missions, they use these same physical principles to accelerate spacecraft by having them approach planets from behind in their orbital motion. For capture to occur, the opposite situation must prevail, with the object approaching Jupiter from ahead in its orbital motion to achieve the deceleration necessary for energy loss. The probability calculations for such capture events, based on statistical analyses of orbital dynamics and the expected flux of interstellar objects through the solar system, reveal their extraordinary rarity. Monte Carlo simulations that model millions of possible interstellar object trajectories through the solar system suggest that successful gravitational capture might occur only once in several million years under the most favorable circumstances, making 3I Atlas an extraordinarily fortunate discovery that provides astronomers with a unique opportunity to study a permanently captured interstellar visitor. The captured orbit of 3I Atlas likely possesses characteristics typical of dynamically captured objects, including high eccentricity that carries the object to great distances from the Sun during the aphelion portions of its orbital period, large inclination relative to the plane of the solar system that reflects its interstellar origin, and potential long-term instability that could eventually lead to re-ejection into interstellar space or collision with one of the planets over timescales of thousands to millions of years. Computer models that simulate the long-term orbital evolution of captured objects reveal the inherently chaotic nature of their motion, with small uncertainties in current position and velocity measurements leading to exponentially growing uncertainties in future orbital predictions over extended time periods. This chaotic behavior arises from the continued influence of planetary perturbations, which create ongoing changes in orbital energy and angular momentum that can either stabilize or destabilize the captured orbit, depending on the specific sequence of future planetary encounters. The implications of 3I Atlas's successful capture extend far beyond the immediate mechanics of orbital dynamics to encompass fundamental questions about the nature of planetary system evolution. The exchange of material between stellar systems throughout the galaxy and the potential role that captured interstellar objects might play in the chemical and perhaps even biological development of stellar systems throughout cosmic history. From an astrochemical perspective, the capture of 3I Atlas offers astronomers an unprecedented opportunity to conduct detailed, long-term studies of pristine interstellar material that has been preserved in the cold depths of space for millions of years before arriving in our solar system. Unlike the brief encounters possible with transient interstellar visitors like Oumuamua and 2I Borisov, which pass through the inner solar system too quickly for comprehensive analysis using current instrumentation, a captured object provides the luxury of extended observation and analysis using increasingly sophisticated ground-based and space-based telescopes. The chemical signatures preserved in 3I Atlas's spectrum, revealed through detailed spectroscopic analysis using some of the world's most powerful telescopes and advanced spectrographic instruments, provide direct insights into stellar nucleosynthesis processes that operated in its birth system, interstellar chemistry that occurred during its extended journey through the galactic medium, and the environmental conditions that characterize different regions of our galaxy. These chemical fingerprints represent a form of cosmic archaeology, preserving information about conditions that existed in distant stellar systems millions of years ago. The organic compounds detected on 3I Atlas's surface through sensitive infrared spectroscopy raise particularly intriguing questions about the potential role that captured interstellar objects might play in distributing life's chemical building blocks throughout the galaxy over cosmic timescales. These complex carbon-based molecules, including polycyclic aromatic hydrocarbons, amino acid precursors, nucleotide bases, and other organic species that serve as fundamental components of biological chemistry, suggest that the raw materials for life are distributed far more widely throughout the cosmos than studies based solely on our own solar system had previously indicated. The detection of these organic compounds in an object that originated in another stellar system provides direct evidence that the chemical processes leading to biological complexity operate throughout the galaxy, creating similar molecular inventories in widely separated regions of space. This discovery has profound implications for astrobiology and our understanding of the potential for life to emerge in planetary systems throughout the Milky Way and beyond. The successful capture of an interstellar object by our solar system also lends scientific credibility to the hypothesis of panspermia, which proposes that life might spread between stellar systems through the transport of microorganisms on interstellar objects that travel between different planetary systems over cosmic timescales. While 3I Atlas itself shows no current signs of biological activity based on spectroscopic observations and the absence of any detectable atmospheric outgassing, its successful journey from another stellar system to permanent residence in ours demonstrates conclusively that the physical pathways exist for organic material and potentially even dormant life forms to traverse the vast distances between stars. The panspermia hypothesis gains additional scientific support from laboratory studies, demonstrating that certain terrestrial microorganisms, particularly extremophils adapted to harsh environmental conditions, can survive extended exposure to the vacuum of space, extreme cold, approaching absolute zero, and high levels of cosmic radiation that characterize the interstellar environment. If such hardy organisms could somehow become incorporated into or attached to interstellar objects during their formation, ejection, or subsequent evolution, the capture of these objects by planetary systems could provide a mechanism for life to spread throughout the galaxy. The competing theoretical frameworks that attempt to explain not only 3I Atlas's capture, but also its specific orbital characteristics and observed properties, reflect the frontier nature of this research, where established physics encounters phenomena that challenge our current understanding of natural processes. While gravitational capture through sequential planetary encounters remains the most widely accepted explanation among the astronomical community, alternative hypotheses deserve serious consideration as part of the scientific process of hypothesis testing and validation. Some researchers have proposed that non-gravitational forces might have played crucial supplementary roles in the capture process, including radiation pressure, effects from solar photons acting on the object's surface, asymmetric outgassing from volatile materials sublimating as the object experienced solar heating during its passage through the inner solar system, or electromagnetic interactions with the solar wind and the complex magnetic environment of interplanetary space. The radiation pressure hypothesis suggests that 3I Atlas might possess unusual surface properties or internal structure that enhance its interaction with solar radiation, beyond what would be expected for a conventional, rocky, or icy body with typical density and composition. If the object has a particularly low bulk density, indicating a highly porous internal structure, or an unusual surface composition that increases its reflectivity to solar photons. The momentum carried by reflected sunlight could exert forces sufficient to contribute to the modification of its trajectory during the capture process. Dr. Loeb's analysis of 3I Atlas incorporates consideration of both conventional and unconventional possibilities, including the remote but logically valid possibility that the object's capture might have involved some form of artificial intervention or technological manipulation by advanced extraterrestrial civilizations capable of precisely controlling interstellar object trajectories. While this suggestion remains highly speculative and currently lacks direct observational support, it exemplifies the importance of considering all logical possibilities when confronting phenomena that occur with extraordinary rarity and challenge our current understanding of natural processes. The artificial intervention hypothesis raises profound questions about the potential prevalence of technological civilizations in the galaxy, and their possible interest in our solar system or similar stellar systems throughout the galaxy. If 3I Atlas represents the result of deliberate technological manipulation rather than purely natural gravitational capture, its presence could indicate that our solar system has attracted the attention of extraterrestrial observers capable of manipulating the trajectories of interstellar objects with precision that far exceeds current human technological capabilities. As we contemplate the future of 3I Atlas research and its broader implications for our understanding of interstellar objects, planetary system evolution, and humanity's place in the cosmic community, we find ourselves at a remarkable juncture in the history of astronomy. The development of next-generation telescopes and space-based observatories promises to revolutionize our ability to study this captured visitor and similar objects that may be discovered in the coming years and decades. The James Webb Space Telescope, with its unprecedented infrared capabilities and exceptional spatial resolution, represents a transformative tool for studying 3I Atlas and other interstellar objects that may be captured or detected in the future. The telescope's ability to observe in infrared wavelengths where thermal emission from cold objects becomes detectable will provide crucial data about internal structure, composition, and thermal properties that are impossible to obtain using visible light observations alone. Ground-based observatories equipped with adaptive optic systems and extremely large telescopes currently under construction will provide complementary capabilities for long-term monitoring of 3I Atlas's behavior, evolution, and orbital characteristics. The 30-meter telescope, Giant Magellan Telescope, and Extremely Large Telescope will offer unprecedented light-gathering power and spatial resolution that will enable detailed studies of surface features, rotational dynamics, and subtle changes in composition that might occur over time as the object adapts to its new environment within our solar system. The potential for future space missions to visit 3I Atlas directly represents the ultimate frontier in interstellar object research, offering opportunities for detailed in situ analysis, surface sampling, and perhaps even sample return that would provide definitive answers about the object's composition, internal structure, and potential biological significance. Such missions would establish technological precedents for visiting other captured interstellar objects and could provide the foundation for future missions to study interstellar objects in their native interstellar environment. As we approach the culmination of our exploration into the remarkable phenomenon of 3I Atlas and its unprecedented capture by our solar system, we find ourselves confronting questions that extend far beyond the specific mechanics of gravitational dynamics and orbital capture to encompass some of the most profound issues facing contemporary astronomy and our understanding of humanity's place in the broader cosmic community. This alien visitor, now permanently bound to our solar system through the invisible but inexorable threads of gravitational attraction, represents far more than a scientific curiosity, an unusual addition to our catalogue of solar system objects, or even a remarkable demonstration of celestial mechanics operating under extraordinary circumstances. The successful capture of 3I Atlas fundamentally challenges our traditional conception of planetary systems as isolated islands in the vast cosmic ocean, revealing instead a galaxy-wide network of material exchange that has operated throughout the 13.8 billion-year history of the universe, connecting stellar systems across immense distances through the patient circulation of matter, energy, and potentially even life itself. Our solar system emerges from this new understanding not as a closed, self-contained entity existing in splendid isolation, but as an active participant in galactic-scale processes that link us physically, chemically, and perhaps biologically to stellar neighborhoods throughout the Milky Way and beyond. The chemical signatures preserved within 3I Atlas's ancient structure, revealed through careful spectroscopic analysis using humanity's most sophisticated astronomical instruments, provide direct, unambiguous evidence of stellar and planetary processes operating in regions of the galaxy that we may never visit directly. These chemical fingerprints transform this captured visitor into a cosmic messenger of unprecedented scientific value, bearing tangible news from worlds beyond our reach and carrying within its crystalline lattices and surface compositions the accumulated history of its million-year journey through the interstellar medium. Each absorption line detected in the object's spectrum tells a detailed story of nucleosynthetic processes that operated in its birth system, of radiation environments encountered during its extended sojourn through the cold depths of interstellar space, and of chemical evolution pathways that have shaped the distribution of elements and molecules throughout our galactic neighborhood. The presence of complex organic compounds, detected through sensitive infrared spectroscopy and confirmed through multiple independent observations using different instruments and analytical techniques, provide compelling evidence that the fundamental chemical building blocks of life are distributed far more widely throughout the cosmos than our Earth-centered perspective had previously suggested. Dr. Avi Loeb's contributions to our understanding of 3I Atlas exemplify the intellectual courage, methodological rigor, and philosophical sophistication that characterize the finest traditions of scientific inquiry in the face of phenomena that challenge established paradigms and force us to expand our conceptual frameworks for understanding the natural world. His willingness to consider both conventional and unconventional explanations for the object's behavior and properties, while maintaining strict adherence to empirical evidence and the logical principles that govern scientific reasoning, demonstrates the delicate balance between healthy skepticism and intellectual openness that drives scientific progress in areas where our current understanding encounters phenomena that exceed the boundaries of familiar experience. Through his careful analysis of observational data, his thoughtful consideration of alternative theoretical frameworks, and his systematic exploration of possibilities that might initially seem extraordinary or unlikely according to conventional wisdom, Loeb has helped establish new methodological approaches for investigating rare astronomical phenomena that require consideration of mechanisms beyond those commonly encountered in standard astrophysical contexts. His work on 3I Atlas continues the intellectual tradition established through his earlier investigations of Oumuamua and other unusual astronomical objects, demonstrating the crucial importance of following empirical evidence wherever it might lead, regardless of how challenging the implications might prove for accepted theories and established paradigms. The international collaboration that has characterized 3I Atlas research from its initial discovery through the ongoing program of detailed observations and comprehensive analysis reflects humanity's collective commitment to understanding our cosmic environment through shared scientific endeavor that transcends national boundaries, institutional rivalries, and the disciplinary divisions that sometimes fragment scientific research into isolated specialties. The coordinated observational campaigns involving telescopes from around the world, the collaborative theoretical investigations that bring together expertise from multiple fields of study, and the open sharing of data and insights across the global scientific community demonstrate our species' fundamental drive to comprehend the universe that gave birth to us and continues to nurture our existence through processes we are only beginning to understand. From a technological perspective, the study of 3I Atlas has driven significant innovations in astronomical instrumentation, computational modeling, and theoretical analysis that will benefit future explorations throughout the solar system and beyond, while establishing methodological precedents that will prove invaluable for investigating similar objects that may be discovered in the coming years and decades as our survey capabilities continue to improve and expand. The advanced detection algorithms developed to identify rare interstellar visitors among the much more numerous population of native solar system objects, the sophisticated spectroscopic techniques refined to analyze their exotic compositions, and the complex orbital mechanics models needed to understand their capture represent substantial advances in our technological and theoretical capabilities that will have applications far beyond the study of interstellar objects. The long-term monitoring of 3I Atlas promises to yield discoveries that extend far beyond the immediate questions surrounding its origin, capture mechanism, and current orbital status, providing crucial insights into how interstellar material evolves when exposed to the very different radiation and gravitational environment of a stellar system. how captured objects respond to ongoing gravitational perturbations from the planets over extended time periods measured in thousands to millions of years, and what ultimate fate awaits these cosmic immigrants in their new stellar homes as the solar system itself continues to evolve and change over cosmic time scales. These long-term studies will be essential for understanding the broader implications of interstellar object capture for planetary system evolution, the distribution and circulation of chemical elements throughout the galaxy over cosmic history, and the potential role that such objects might play in distributing the building blocks of life between stellar systems over time, scales that encompass the entire history of the galaxy. The accumulated data from years and decades of continued observation will also help refine theoretical models of gravitational capture mechanisms, improve our ability to predict and identify future capture events, and perhaps most importantly, deepen our understanding of the interconnected nature of galactic evolution and the processes that govern the emergence and distribution of complexity throughout the universe. The story of 3I Atlas ultimately transcends the boundaries between scientific disciplines to encompass questions that touch our deepest philosophical concerns about existence, connection, and belonging in the cosmic context that shapes all aspects of our reality. This remarkable object, transformed from interstellar wanderer to permanent solar system resident through the complex choreography of gravitational forces operating across vast scales of space and time, embodies universal themes of journey and arrival, of finding home in unexpected places, and of the fundamental interconnectedness that underlies all phenomena in the universe. Themes that resonate across scales from the cosmic to the intimately human and speak to our deepest longings for understanding and connection. In our quiet moments of reflection, as we contemplate the implications of this alien visitor's permanent residence in our gravitational neighborhood, and consider what its presence might mean for our understanding of our place in the universe, we might pause to appreciate the profound interconnectedness that underlies the apparent isolation of stellar systems throughout the galaxy, and recognize that 3I Atlas serves as a cosmic messenger that reminds us of our participation in processes of galactic scope, connecting us not only to distant worlds, but to the fundamental forces and evolutionary pathways that have shaped the universe throughout its long and continuing history, making us citizens not just of Earth or our solar system, but of the entire galaxy that gave birth to the elements in our bodies and the cosmos that encompasses all matter, energy, space, and time.